In this video, we're going to solve a double integral, and we're going to use a somewhat interesting trick called changing the order of integration. The idea is as follows. In this double integral that I have, there is a specific order of integration that is implied by the fact that it says dy dx. That means that we're supposed to integrate with respect to y first, and then we're supposed to integrate with respect to x. So there's sort of an inner integral with respect to y, and then an outer integral with respect to x. Now, the problem is, I actually can't integrate that inner integral. I can't integrate with respect to y, because the integrand, this 1 over y to the fourth plus 1, I don't know how to integrate that. If it was 1 over y squared plus 1, I could integrate that and get arctangent. If it was, say, y cubed over y to the fourth plus 1, I could do a u substitution. But it's not obvious to me that there's a method to integrate with respect to y the function 1 over y to the fourth plus 1. And if this was first-year calculus and we were just asked to do the inner integral, then we'd be kind of hooped because we wouldn't have an obvious approach. But in multivariable calculus, we're allowed to change the order of integration if it helps us, and it will in this particular example. So in order to change the order of integration, to do an integral with respect to x first and then do an integral with respect to y, I'm going to have to correspondingly change all the limits of integration, which are right now written as cube root of x up to 2 and 0 up to 8. So my process is going to be this. First, I'm going to try to interpret what the region that is implied by these limits of integration are. And then secondly, I'm going to rewrite that integral with the order reversed by looking at the region that we just determined. And hopefully that will be easier for us to integrate. So looking at these limits of integration, the most interesting part is the cube root of x. Everything else is just a constant. So I'm just going to try and plot the cube root of x. It looks like this. And I sort of think that that means that I've got some correspondence here between the lower bound in my integral with respect to y, the function y equal to cube root of x, and well, I put that on the graph. And then what it's saying is that y is going from this cube root of x on the bottom up to the value of y equal to 2. And so I'm also going to come here and I'm going to put y equal to 2 on the same plot. So this inner limit of integration between cube root of x and 2 is basically saying that is all the y values. And I may as well just sort of fill it in. This is the region that I want to look at. Now, I also have to make sure that the x limits of integration also correspond with this region that I've drawn. Otherwise, perhaps it needs to be a little smaller or a little bigger. But nevertheless, if I look at the top limit, which is the 8, this is saying that x is equal to 8. That's the right bound here. So I'm going to draw the line x equal to 8, but it actually sort of doesn't matter because the graph of y equal to 2 and y equal to cube root of x, they happen to be aligned at the value of x equal to 8. Then on the left-hand side, the smaller value of x is just going to be 0, and so indeed it just starts at that y-axis. So what I have is this nice region that is implied by the limits of integration. I also want to note that because I'm doing the integral with respect to y first, and then the integral with respect to x, the approach to integrating this I'm using is to first use vertical strips. I take a generic x value, and at that generic x value, I am integrating with respect to y from the bottom curve, the cube root of x, up to the top curve, the y equal to 2. So I always like having these sort of dotted lines to help signify in my mind that we're doing vertical strips, and then this vertical strip will be integrated with respect to x after that. So if I want to switch the order of integration, let me instead take a generic horizontal strip. Everything else is exactly the same. It's just now I'm thinking about first integrating with respect to x and then integrating with respect to y. Okay, so how can I write this in my new integral? So let me clear out the limits of integration. We have to fill those in. And I have also reordered. It is no longer dy dx. It is now dx dy. I'm integrating with respect to x first. That's why I'm using these horizontal strips. So I have 4 numbers to fill in, the lower bounds and the upper bounds for each of these 2 integrals. Let's do the one with respect to x first. So the lower bound with respect to x, the inner integral, well, what's the smallest value of x that we see here? Well, it's just going to be the value of x equal to 0. That's the lowest possible value of x. And then if I go along that horizontal strip, and then if I walk along that horizontal strip, which keep in mind is at just some generic y value, some generic height, but if I walk along at just a random one, the end point, the furthest right point that I get to is, well, it's this point on the curve y equals cube root of x. The only thing is, I don't want to put y equals cube root of x into my upper limit of integration because this is supposed to be written as, it's an integral with respect to x. It's supposed to be written as x equal to something. So if y equals cube root of x, then x is equal to y cubed. That is, I'm just solving the same equation, but for the other variable now. It's always a good rule of thumb that when I think about the inner integral, the one that's dx, that's with respect to x, that means its limits of integration should be written as x equals something and x equal to something else. So it's important to always solve for x equal to, in this case, y cubed. All right, so that was the inner integral with respect to x. Now let's do the outer integral with respect to y. At the bottom, it's just going to start here at 0. That's the lowest possible spot in this region, and the highest spot in the region is going to be 2, and so I just put in 0 and 2. Okay, so that's my new integral. I can sort of forget the region. All of that analysis of the region was to go from our original integral, which was a dy dx, interpret the region, and then I wrote down this new integral from that region doing horizontal strips versus vertical strips. But now I can sort of forget that. Now it's just a computational problem. I have some double integral, and I'm returning to the question, can I do it? But this time, I can. And the reason is that the first integral I should do, the inner integral, the integral with respect to x, well, the integrand is just all some function of y. It's a constant with respect to x. And so it's very easy for me to do the inner integral. So what is it? The 1 over y to the 4th plus 1 is just a constant. It just comes out. And then I just have to plug in the y cubed on the top and the 0 on the bottom, which I can ignore. So just doing that inner integral is just very straightforward. And now this integral with respect to y that I've gotten is now doable. Now I've got a y cubed on the top. And that was the thing we didn't have before. We didn't have this y cubed in the integrand. Because now I can just do u substitution. I can just say u is the denominator, y to the 4th plus 1. So du is 4y cubed dy. And I have that y cubed there. So what do I get? This is just going to be 1/4 of the logarithm of the denominator. So in other words, 1/4 of the logarithm of y to the 4th plus 1. I'm evaluating it between the endpoints of y equal to 0 and y equal to 2. When you plug in those numbers, you just get the logarithm of 17 divided by 4. So the moral of this particular double integral is that sometimes when you've written a double integral down, you cannot do it easily by algebraic methods. But perhaps you can reinterpret the region that are implied by the limits of integration such that you can talk about the same quantity, but with the order of integration reversed. And maybe you get lucky. Maybe reversing the order of integration transforms it from an intractable integral to one that you can actually do.